Okay, so we're going to start with our direct variation. So, like I said, direct, inverse, and joint are all going to be your 8.1. We're going to do some straightforward problems, and we're going to do some word problems also, okay? So, direct variation, that is something you should have gone over in Algebra 1, which is just y equals kx or y equals ax. I think Algebra 1 we typically do a. That k, or if you would have learned a, is your constant of variation, okay? And it will not equal 0. So your keyword to know the difference, if it says y varies directly, that's your direct variation, okay? To me, that's very straightforward. You just have to know which formula it is, okay? So if y varies directly with x, so that's your y equals kx, and y equals 9 when x equals 15, find y when x equals 21, okay? We are not setting up equal proportions or anything like that. We are plugging in your original x and y. You're going to solve for that k. Alright, so if I have y equals 9 and x equals 15, I've got 9 equals k times 15. If I need to solve for k, I'm going to divide by 15. So k would equal 9 over 15 simplifies, that's a negative. 9 over 15 simplifies to what? 3 over 5. Alright, so my equation is y equals 3/5 x. I want to see this before you plug in that 21. Okay, that's going to be half of your answer. Alright, now I'm going to plug in 21, so y is equal to 3/5 times 21. And what is that going to give you? Should be 63/5. These problems are literally plugging in numbers, solving for your unknown, making your equation, plug in another number, okay? So now, if we've got joint variation, this is where you've got y equals k times x times z. So now you've got 3 variables. K is still and always going to be your constant of variation. So if y varies jointly as x and z, whatever is varying with the others is going in the y spot. So if I change the variables, okay, if I said a varies jointly with b and c, it would be a equals k times b times c. If z varied jointly with x and y, then it would be z equals k times x and y, okay? So pay attention to that wording. Whatever is varying jointly or directly or inversely is going in this spot, okay? You might have problems where it mixes up the variables, so that's why I'm saying that, okay? So y is 96, z is 4, and x is 8. So I'm going to have 96 equals k times 8 and 4. Alright, so 96 is equal to 8 times 4 is 32. Okay? And so, divide by 32, and k is equal to. So y is equal to 3 times x times z. That's your first part of your answer. So then when we want to know what y is when x equals 7 and z equals 12. So y is equal to 3 times 7 times 12. Which gives you, thank you. Okay, now with inverse variation, y is equal to k divided by x. K is still your constant variation. X cannot equal 0 because your denominator cannot equal 0. Okay, so if r varies inversely as t, and r is equal to 18, and t is equal, when t is equal to negative 3, find r when t is equal to negative 6. So this time, instead of y and x, I'm going to have r is equal to k over t. So I'm going to have 18 is equal to k over negative 3. So k will equal what? $18 times negative 3. So r equals negative 54 over t would be my first equation. So find r when t is equal to negative 6. So r is equal to negative 54 divided by negative 6, which is 9. Okay, so now it says y varies inversely with x. Use the given values to find the constant of variation. Then write an equation relating x and y. Finally, find y when x equals 5. That's a whole bunch of words just to tell me what we were just doing. Okay, so even though it looks like it's set up differently, the problems are still the same. Y varies inversely with x, so that means it's y equals k over x. Alright, so y is 3/2. X is negative 4. So multiply both sides by negative 4. 3/2 times negative 4 is going to give me what? So k equals negative 6. So I've got y equals negative 6 over x. And I want to know what y is when x equals 5. So y would just equal negative 6 over 5. I can't do anything with that. Okay, do we have questions? Alright. Now a word problem. As long as you're picking out your key words, the word problem is not hard. It says the volume of a gas varies inversely as the pressure P. So without doing anything else, what's my formula going to be? V equals K over P. Use the variables that your problem gives you. Okay, if the volume of a gas is 240 cubic centimeters under a pressure of 20 kilograms per square centimeter, what is the volume when the gas is placed under a pressure of 24 kilograms per square centimeter? So my volume is 240 equals K over 20. So that would make K equal to 4,800. So my volume is equal to 4,800 over my pressure. So what is the volume if the pressure is 24? Two hundred what? Make sure you have your units if you're doing a word problem. Okay, we good with that? Alright. Okay, moving on to part 1 of 8.2, where we are graphing rational functions. Okay, a rational function can be in the form of f of x equals p of x over q of x. And what does that mean? Basically, we just have a fraction. Okay? So the parent function of a rational function is just f of x equals 1 over x. So since we have fractions, we've got rational functions, we're going to have to do restrictions. Okay, why do we need a restriction? Well, if you think back to inequalities, okay, what we just did, you couldn't have a negative underneath the square root, right? It would give you imaginary. So we would take what's underneath the radical, set it greater than or equal to 0 and get a restriction. Y'all remember that from chapter 6? Y'all didn't just now do that, but that was chapter 6. Okay, when we did radicals. So that's your restriction because we don't want an imaginary number. Here, when you have a fraction, what do you think is going to cause a restriction? The numerator or the denominator? The denominator. Okay? When you are dividing, you cannot divide by 0, right? You get undefined. So whatever your denominator is, you're going to have a restriction on the domain by setting that denominator equal to 0. Okay? That's your restriction. That's going to lead to your vertical asymptote. So whatever that restriction is will be your vertical asymptote. So if I have f of x equals 2 over x minus 4, okay, we're going to set that denominator, x minus 4, and we're going to say it cannot equal 0. We're going to solve for that x, though. So I would add my 4, x cannot equal 4. So that is my restriction on my domain. Which leads me to my vertical asymptote being x equals 4. If x cannot equal 4, there's my asymptote. Okay? Now, we're going to have vertical and sometimes the horizontal asymptotes in the same problem. So what happens is the horizontal asymptote is going off of the degree of your numerator and the degree of your denominator. These are things you're going to have to memorize. Okay? You're going to have to memorize your rules. Okay? So it says if the degree of the numerator is greater than the degree of your denominator, you have no horizontal asymptote. Okay, well, what does that look like? So that would be something like f of x equals x squared minus 3 over 2x. Okay, something like that. The degree of my numerator would be 2. The degree of your denominator would just be 1. Okay, so I would have no horizontal asymptote. Now, if the degree of the numerator is equal to the degree of the denominator, then you're going to set up a ratio of your leading coefficient of the numerator and denominator. Okay, so if I had f of x equals 4x squared minus 5 over 3x squared plus 1. Okay, well, my degree for both would be 2. So what I would do for my horizontal asymptote, I would have y equals, my leading coefficient for my numerator is 4 over the leading coefficient of my denominator is 3. So it would be y equals 4/3. Okay. Now the last one, if the degree of your numerator is less than the degree of your denominator, then it's just y equals 0, regardless of what the numbers are. If I have f of x equals 5x over 2x squared plus 1, my numerator is less than my denominator, so it's just y is equal to 0. Okay? So we're going to look at it. Okay? We're going to do all three of those things. We're going to do the restriction, we're going to do the vertical asymptote, and we're going to do the horizontal asymptote. Okay, so for my restriction, I've got to set my denominator, x plus 2, and it cannot equal 0. So x cannot equal negative 2. And that leads me to my vertical asymptote being x equals negative 2. Alright, then my horizontal asymptote, my degree of my numerator is what? 1. My degree of my denominator is also 1. They're equal. So I set up a ratio. it's just a coefficient of 1 over a coefficient of 1. It's just going to be 1. Okay? Now for the next one, I've got f of x equals negative 3 over x minus 3. X minus 3 cannot equal 0. So x cannot equal 3. Which leads me to my vertical asymptote being x equals 3. Now my horizontal asymptote, my degree of my numerator, I don't have an x. So that's 0. If it's just a constant, then my degree is 0. And then my degree of my denominator is 1. So my numerator is less than my denominator. So my rule tells me it's y equals 0. Okay, I want you to know something. This isn't going to happen on this lesson, but for 8.2 part 2 it will. Your vertical asymptote and your horizontal asymptote, you treat differently, okay? I've told you your asymptote is what your graph approaches but never actually crosses. So that is a broad explanation of what an asymptote is. Because next lesson we're going to learn that you actually can cross a horizontal asymptote. Why can you cross a horizontal but not a vertical? Think about where you're getting these asymptotes, okay? A vertical asymptote comes from the restriction on the domain. So I'm not going to have that no matter what. I will have an asymptote that I can't cross. But a horizontal asymptote is just based off the degrees of your numerator and your denominator. That's not a restriction necessarily. Okay, so next lesson we're going to learn you can cross horizontal asymptotes because the mathematical definition is not that broad description I just said. It approaches but never crosses, right? When you get to calculus, you'll get the actual mathematical definition that goes with the limits. Okay? So I'm just giving you a heads up. We're not focusing that on this lesson, but next lesson we're going to determine if it crosses or not. Okay? Alright, graphing simple rational functions. So what we're going to do is we're going to look at our restriction, we're going to notate what our asymptotes are, we're going to graph it in our calculator, grab some of the points from the table. You want enough points to give you your shape. Okay, so I say about 4 or 5 points on each side of the asymptote. Draw it and then state the domain and range. Okay, so my first part, we got to look at our denominator. X cannot equal what? X minus 3 cannot equal 0, so then x cannot equal 3. Okay, so then that tells me my vertical asymptote is x equals 3. My horizontal asymptote, what's my degree of my numerator? And the denominator? They're equal, so I set up a ratio of my coefficients. My coefficients are both 1 and 1, so my horizontal asymptote would be y equals 1. Okay, before I even do anything, I'm going to go ahead and do my dashed lines for x equals 3 and y equals 1. Then I'm going to go to my calculator, clear it if it hasn't already been cleared. In your graph, control divide will get you your fraction. And then we're going to graph x minus 1 over x minus 3. So, if you notice, the more negative I get, the bigger my decimals are, right? So all they're doing is getting closer and closer to this y equals 1. You don't have to include every single thing, all right? So I say you can include -1, 0.5. You can do your 0, 0.3. If you want to adjust your table, just know you can if you do menu, table, and then table settings. Okay, I'm not going to do that right now, but if you hit menu, you can navigate your way to adjust those settings. Alright, so then 1, 0, 2, -1. 3 is going to give you that undefined because that's where you're dividing by 0. That's why it's an asymptote. Okay? And then you're going to have 4, 3, 5, 2. I'll just skip 6 and do 7, 1.5, and that should be enough. Because all it's going to do is come back really close to 1, but never actually get 1. Okay? Y'all good with how to get points for your table? Okay. Okay, so once I graph that, I need to state my domain and range. My domain is my all possible values for my x, right? So I'm going left to right. My only restriction on my domain is x cannot equal 3. So that means I'm going from -infinity all the way to that asymptote. I can't have 3. Okay? So if I were doing, say, interval notation, I'm going to go from -infinity to that 3. I'm not going to have a bracket because that's an asymptote. Then I'm going to have my union symbol and pick it back up at 3 and go to +infinity. So with it being parentheses instead of a bracket notates that it's not equal to 3. Okay? Now if I were doing set builder notation or just a basic inequality, you'd be having all real numbers except x cannot equal x cannot equal 3. Okay? So for now we're just going to do interval, but if you're doing something else it would just be x cannot equal 3. Okay? Now for my range, all possible y values, so that's going from bottom to top. So my only restriction for my y's is where? My horizontal asymptote. It didn't cross it. There's my asymptote, so I'm going from -infinity to 1, and then picking back up at 1 and going to +infinity. Again, you're doing parentheses because it's not equal to. So your domain is off of your vertical asymptote. Your range goes off of your horizontal asymptote. You're good with that? Alright, so now, what if we have transformations? Every single function you have a transformation, okay? So now what if it looks like f of x equals a over x minus h with a number tacked on at the end, okay? If you have something tacked on at the end, you're no longer going to do your horizontal asymptote based on the numerator and denominator degrees. Okay? So this is set up to tell you my vertical asymptote is x equals h. My horizontal asymptote is y equals whatever is tacked on at the end. Okay? If there is nothing tacked on at the end, it's 0. Okay? Because it's plus or minus 0. So you're going to have to know what it looks like and what do you do for your asymptotes based on what it looks like. Okay? Now we still need a restriction, right? X cannot equal what? X cannot equal -2. Well, if you notice, that's still going to be my vertical asymptote. Okay? Your denominator restriction will always be your vertical asymptote. But now my horizontal asymptote is going to be y equals -1. So I'm going to plot those dashed lines. I'm going to go graph. Be careful how you type it into your graph. So if you didn't go all the way down to -10, that would be okay. I would not count points off, but I would go there because I can fit it. Okay, so I'm going to have -10, -0.5, and I'd probably skip to that -7, -0.2. It's okay if you skip around. Then -6, 0. -4, 1, -3, 3. Then I'm going to have my -2 undefined. It's your asymptote. -1, -5, 0, -3, 2, -2. And then I'd probably jump to 6, -1.5. All of those decimals are pretty much the same, so I'm not going to just keep writing the same rounded decimal. And so I could stop there. So then my domain My only problem area is where? -2. So I'm going to go from negative infinity to -2, and then pick back up -2 to positive infinity. And then my range will be what? And then, very simple. Okay, we have questions on that? All right. So with rational functions, you have the possibility to have a removable discontinuity. Okay? So what happens is if I give you a function and I can factor it. Okay? So if I have x squared minus 25, I should automatically recognize that that's the difference of two squares. Okay? So that could factor x plus 5 times x minus 5 all over x minus 5. So what do you recognize when I put it in factored form? Those x minus 5 factors cancel out. That's your removable discontinuity, or point of discontinuity. Okay? So what happens is, instead of having a vertical asymptote here, it's the removable discontinuity that factored canceled. And so my factored form, or simplified form, is f of x equals just x plus 5. Well, now, that's a linear function. It looks a whole lot more complicated than what it is, but when you simplify it, it's just linear. Okay? But if I just remove something, I have to account for that. So what I'm going to do is that point of discontinuity, I'm going to get the x by knowing what can that not equal. Well, originally we would say x cannot equal what? A 5. Right? That would be my restriction, my original restriction. Okay? Well, the only way I can account for this removable discontinuity is put a hole in my graph at that x equals 5. Well, how do I know exactly what point it is? I'm going to take this and plug it in to my simplified form. So I'm going to find f of 5 is 5 plus 5, which is 10. So I'm going to have a hole at 510. That is my removable discontinuity, or point of discontinuity. Okay? It's more commonly called the point of discontinuity, but when you get to Miss Baker's class, she doesn't really call it that, because if you have a piecewise function or something, you could have a point there, so it's really not, if you're doing domain, it can get a whole lot messier than just this. Okay? So I'm going to teach y'all to know that terminology. It's just a removable discontinuity, or a hole. Okay? So at 510, I'm going to put an open circle to notate that that's my hole. I did that at 410 because I can't count today. Okay, there's 510. My bad. So how am I going to graph this line? Well, you've got the graphing calculator, but you shouldn't have to. You should know how to graph x plus 5. My y-intercept is where? 5. And I go up 1 over 1. So I'm going to draw that line. You can either use your ID or get a ruler later. You're not going to have that's every single problem, so I would just use your ID. You should all have it anyways. So just a typical line with a hole at 510. So then my domain would be all real numbers except x cannot equal 5. Or interval notation would be negative infinity to 5, and then 5 to positive infinity. Now range would be all real numbers except x cannot equal 10. So interval notation would say negative infinity to 10, and then 10 to positive infinity. Okay? Questions on that? It's simple. Okay? So you're not going to have a quiz over just this one. When I teach y'all the second part of 8.2, you'll have a quiz over 8.1 and all of 8.2. Okay?